So continuing with this idea of correlation, we're going to look at what's called the Pearson's correlation coefficient. So line of best fit, fantastic. But it's very subjective, of course, because you're doing it by eye, and we're all going to get different lines unless something amazing happens. But that's not what we like in maths. We like exactness, preciseness. Pearson's correlation coefficient. So the symbol we use, if we're talking about a sample of data, it's R. If it's population data, we use the Greek letter rho. But what you will notice is when it's population, we tend to use the Greek alphabet. When it's population, we use the Latin alphabet. Okay. All right. Let's keep going. There's our formula. Whoa. So you're comparing two bits of data, so two random variables. You've got X and Y, two different random variables. So it's what we call the covariance over the standard deviation of X, standard deviation of Y. Variance was the expected value of X minus the average squared. Well, covariance, instead of squaring, we just take the two and multiply it together. So the units are still the same. So we have X minus X bar and Y minus Y bar. That's how covariance is worked out. What it basically means is we can work out covariance by saying, well, it'll be the average of when we multiply the X and the Y together minus the average of X times the average of Y. And as we saw yesterday, it should always be in between minus 1 and 1. If it is 1, then that's that perfect correlation. Line, a beautiful straight line. Very unusual for it to happen. In between 0.6 and 1, we say strong correlation. 0.4 and 0.6, moderate. 0.1 and 0.4 is very weak. 0 to 0.1, well, there's virtually no correlation at all. And of course, 0 itself means there is no correlation. The sign just basically tells you which way they're correlating. So positive means as one increases, the other increases. If it's negative, then it's going the other way around. As one increases, the other decreases. Let's use this example. Now I'm only using 8 pieces of data for the sake of the example, because if I was to do heaps of data for this example, there'd be a heck of a lot of calculations we'd have to do. So 8, we'll do it that way. So 8 people, and we found out their birth weight, but also their weight when they reach the age of 21. We were interested in seeing, is there some correlation between these weights? Do heavy babies become heavy 21-year-olds? Things like that. So first of all, construct the scatter plot of the data, and from the plot, how would you best describe the association of the data? There's our plot. It does look like there's a linear correlation. It's sort of linear there. That'd be my best representation. Calculate the coefficient for this data. Alright, if ever we had to do this, this is what we would have to do. 2 random variables. One's going to represent birth weight, one's going to represent the weight at age 21. We will put it into a table. So we're going to have now a row for both the X values and a row for the Y values. Sum them up, because the sum column is going to be handy. I'm also going to now need X times Y, because remember that covariance formula had X times Y in it. So let's work out what X times Y is and sum that up. X squared and Y squared, that's going to come in handy, because when we worked out expected value and variance, that involved X squared. So we'll work that out. Okay, average. X average will be 22.7 divided by 8. We've got 2.8375. Average of Y we can work out now, 54.825. We can find the average of XY, 157.025. Okay, what else do we need? We need to work out our deviations. Before we can work out deviations, we have to work out variance. So on the X's, so the average of X squared minus the average of X squared, 0.5219. Now we'll do it for Y. Okay, I think that's enough for our formula. Let's sub it in. 0.7862 ends up being the correlation coefficient, which fell in our category of, I think that one was strong, wasn't it? So we do indeed have a strong correlation with this data. So that now brings us to what we call the least squares regression line. So it's getting this straight line, but all of us getting the same straight line. It's known as linear regression. we'll fit it to an exact straight line here. Now, it assumes, of course, we're dealing with linear correlation. Otherwise, how would we get a line if it's not linear correlation? And it works the best when you don't have outliers. Outliers can really screw this stuff up. And that's why we often exclude outliers, just to make life easy. Right? This is what it aims to do. It minimizes the sum of the squares of the distance. Actually, remember, you're trying to fit it so that it's right in the middle of all this data. And so the gaps, we would like as close to the line as possible. So we want to minimize it. Why the squares? Well, by squaring it, I'm ensuring I've got a positive number. And so it doesn't matter whether it's above the line or below the line, I can still compare all those distances and get it the same. We guarantee that it will pass through that point there. Average x, average y. That's one thing we make sure of. Therefore, what happens is this. The least squares regression line, its slope will end up being the covariance of xy over the variance of x. It's like rise over run. Well, we can substitute into that and make it a little bit easier. That means it's going to be the average of xy minus average of x times average of y over the variance of x. But I can tidy that up as well if I play around with those formulas, and it simply becomes this. That correlation coefficient that we worked out times the deviation of y divided by the deviation of x. The y-intercept, well, it'll end up being that. It's just the equation of the line rewritten if you look at it. Because remember, we guaranteed it would go through the point x bar, y bar. So rearranging it, we work out what the y-intercept is. So draw the line of best fit and find its equation. So this one I'm doing by eye. Let's see how good my eye is compared to the one that the formula would work out. I went with that one. Now I deliberately made sure it went through a point I could read off nice and easy. So you see how it goes through the intersection of these ones? So I might have cheated a little bit there to get my line of best fit. I wanted to make sure I could get through a point like that. So I need to know 2 points on the line to find the equation of the line. And oh look, it goes through 250. That was nice. The other point, what did I pick? Oh, down here when it's 40. And I probably got a ruler and measured for that one. 0.275, 40. So there's my slope and there's my equation. So I'm saying that's the equation of the line. But now we're going to find the least squares regression line, and let's compare the two, see how good my eye is. There's the formula for the slope, and we've calculated all those things already. So 5.36 for the slope. What did I say it was? 5.79, okay. Work out the y-intercept, 39.616. There's the actual one. 5.36x plus 39.62. Okay. If I was to now draw that, I know it goes through a couple of points. I've got an equation. I can find as many points as I want. So I've picked one there and one there. Not too bad. It's pretty close. Let's have a look at an HSC one. This is what they asked in the very first one. Right? The famous cricket question. No, not cricket. Cricket, the insect. Right? So a cricket is an insect.
Really?
Just to make sure. The male cricket produces a chirping sound. Now a scientist does what scientists do, and they want to explore the relationship between the temperature and the number of chirps from a cricket in a 15-second time interval, because this is what scientists do. Once a day for 20 days, the scientist collects the data. And based on the 20 data points, they got this information. So this is the information they were provided with in the HSC. They had a lovely box plot of the data. Right? And I guess that made sure they knew how to read box plots. Then this information. Well, the mean temperature in the data set is 0.525 degrees Celsius below the median temperature. And there were a total of 684 chirps collected when they got their 20 data points. So this is all the information they were given. Oh, fortunately the scientist has worked out the formula for us already. So least squares, oh hang on, we don't know what B is though. Ooh, that's annoying. So we've got to find B. But anyway, question keeps going. The least squares regression line passes through, well, we know that. So again, they're helping them out because they're even telling them that, hey, remember, this line will go through this point. Has to go through this point. And just in case they were unsure what X bar is, where X bar is the mean and Y bar is the mean, I suppose they needed to know which one was the X, which one was the Y. And here's what they had to do. Calculate the number of chirps expected in a 15-second interval when the temperature is 19 degrees. Well, they gave me some information. Remember they told me that the average was 0.525 below the median. That allows me to work out X bar. So I've got that. Y bar we can work out because they also gave me some information that there were 684 chirps all up. So divided by 20, average of 34.2 chirps. We now know the regression line must go through that point. Well, that will allow us to find B. Substitute that into B. Look at the numbers. They're not nice, but B is going to be this division. I didn't worry about finding that because I figured it's going to be such a long decimal. I thought I'll leave it as that fraction because essentially I just want to know what Y is when X is 19. So I left that fraction. I thought, well, we'll do the calculation all in one hit. And we end up with 29.036060888. So, okay, 29 chirps is what we'd expect. So that is the question they asked on this stuff in the HSC. All right, now, 15E, you'll see I said, for a bit of fun, actually use the formula. Go and try and work it with the formula.